Hi everyone, I'm Tavor Bharov, and today I'm going to be talking to you today about Bandit-based Monte Carlo optimization for nearest neighbors. So today I'll be presenting joint work with my collaborators Vivek and Govinda, who did their PhDs at Stanford, and my advisor David Che. So first, to formulate the problem, I'll be discussing the querying version of k-nearest neighbors, where we have a data set of endpoints in RD, and a new query point arrives, and we want to find its k-nearest neighbor among this set of endpoints. You can consider most common distance metrics for the sake of this talk, but for concreteness, let's focus on L2. The issue with brute force is that it becomes computationally inefficient as the dataset grows. That is, with a naive method, you need to, for each point in the dataset, compute your exact distance to it. Right? Distance computation is order D time. To combat this, there's been a lot of recent work on reducing this, on kind of lowering the bar to make it an approximate nearest neighbor problem, and there have been fast algorithms for this, like locality sensitive hashing, which makes it so that you only need to compute your exact distance to a subset of points in the dataset. However, note that this still has linear dependence on the dimension D, which in modern datasets, let's say for genomics, can get to be very high dimensional, and this is still prohibitively expensive. For example, in this 10x genomics dataset, we have gene expression vectors in 28,000 dimensions. So how can we hope to get around this? Well, considering the simple problem of finding the one nearest neighbor of the query point x0 under L2 squared distance, we see that we can rewrite this problem as argmin over I in n of theta I, where theta I is just expanding out the Euclidean squared distance and adding a 1 over d normalization factor out front. Now, almost tautologically, what we can say is that if I look at the distance between xi and x0 on coordinate j, where j is chosen uniformly random on d, then in expectation, this is exactly theta I. So again, this seems like a very simple observation, but what it gives us is a way to generate unbiased estimates of theta I, which we can do independently. And what can we do with independent unbiased estimates? We can average them to get better estimates. And so with this primitive in hand, what we can do is take this computation problem of exactly computing n sums, n distances, and reduce this to a problem of statistical estimation, where we're trying to estimate the means of n random variables and pick the one with the smallest mean. And so now we have a randomized algorithm with some error probability. However, if you noted, in the previous slide, we said take m terms for each sum. That is, compute each estimate of distance to the same degree of accuracy. But we don't need to do that. In reality, all we need to do is to determine the argmin. We don't get any extra points for getting everyone to the same accuracy. And so we should only sample them to the necessary accuracy. That is, points that are far away, we can only get a coarse estimate of their distance, whereas very close points, we should kind of estimate their distance much more well, so that we can tell who is actually the nearest. Thinking about this problem a little bit more broadly, we have query access to n random variables, and we want to find which one has the smallest mean using the fewest number of samples. This is exactly the best arm identification problem in multi-arm bandits. So I spend most of my time here on the bandit reduction and not on the actual k-nearest neighbor algorithm, but I'm happy to discuss those later if you want. I just think that that's the kind of cool 5-minute takeaway that if you leave with anything, hopefully you leave with that. But specifically for k-nearest neighbors, we use a simple upper confidence bound-based algorithm, and we're able to improve upon brute force computation dramatically. There are other instances of people using this reduction from computation to adaptive statistical estimation. I've cited some works below. We don't yet have a publicly available preprint, but that should be available soon. And generally, please contact me if you have any questions, or I'm happy to answer them in the session afterwards. Thanks so much.